Anyways, I'm going to go ahead and start. So again, I'm Ann Anderson, and this is a picture from our campus. I'll talk more about this building. And as Professor Buratti said, we are here as part of the Fulbright Specialist Program. Okay. So just an overview. So today, the first bit, we're going to introduce ourselves and where we're from. And we'll talk about an introduction to aerogels. And then Mary will do an introduction to sol gel chemistry. Tomorrow, I will talk about aerogel drying methods. And on Thursday, Mary will talk more about the chemistry of aerogels. And then over the next few weeks, as I'm here, these are some of the topics that I identified to talk about, all related to aerogels. Okay, so Professor Buratti introduced me, but again, my career, I am a mechanical engineer, and I got a bachelor's degree from Tufts University, which is a school in Boston. And then my master's and PhD at Stanford University, which is an opposite side of the country in California. Before becoming a professor, I worked at IBM. This is before I learned about aerogels. I designed cooling systems for computers for a couple of years. And then I started at Union College, and I've been at Union since 1992 in mechanical engineering. And I'm also a chief technical officer of a company that Professor Carroll and I founded called Sun-Through LLC. And we'll talk a little bit about that. My expertise is in fabrication, characterization, and applications of aerogel materials. I am not a chemist, so you have to ask your chemistry questions this week for Mary. My background and my PhD is in heat transfer and fluid mechanics, experimental methods, and I did some work with liquid crystal thermography. Mary.
Okay, so I'm a chemist, so my background is in chemistry. I earned my bachelor's degree from Union College, where we both teach now, and then went to Indiana University in Bloomington, which is in the Midwest part of the US, for my PhD in analytical chemistry. I then did postdoctoral research at the University of Massachusetts at Amherst before returning to Union as a faculty member, and I've been in the chemistry department since 1992. As Ann mentioned, we have a startup company called Sun-Through LLC, which we have formed and which we are involved in. And my most recent exciting news is that I am one of two candidates for the 2023 American Chemical Society president-elect, which means if I am elected in the fall, I will be president-elect in 2023. I will be the president of the ACS in 2024. And past president in 2025. That's assuming I'm elected, which is not a guarantee. My expertise is obviously also in aerogel materials. We have been collaborating, Ann and I, for about 20 years. My prior research focused on experimental molecular spectroscopy, and we still do some spectroscopic applications for sensing and things like that with aerogels. Background in chemical sensors, dye interactions in solution and sol gels. And one of the things I did in experimental molecular spectroscopy is build instrumentation. That is not something that we are currently doing. We are focusing on the aerogel materials. That's a little bit about me, and now back to Ann.
Okay, so we thought just for the first bit here, we would do a little bit of an introduction of where we are from and about where we're from. And then we're actually going to ask all of you to tell us a little bit about you. So where we're from is New York State. So this is a map of the United States. And we're up here in the northeastern part of the country. Mary went to school in Indiana. Which one is this?
That's Indiana.
Pretty good. I don't know. I know it's one of those states in the middle, and I went to graduate school out here in California. But we're both back here in New York State. This is a map of New York State. It's a big state. It's one of the largest states in the United States, population, it's top three or four. Our big states are California, Florida, New York, yeah, and Texas. So most of you probably know about New York City. Whenever we tell people we're from New York City, people outside of the US who are from New York, they say, oh, New York City. So everybody knows New York City, but we're not from New York City. So New York City is down in the southern part down here. Schenectady is just north of New York City, about 2.5 hours by train. I don't know how many miles. 150 miles, how many kilometers? 300, 250 or 300 kilometers. And we're up here. And so we're at an area, there's another state here, Vermont and Massachusetts and Connecticut. So we're near other states. So the origins of Schenectady is that it was populated by Native Americans originally, and and we know this is young for Italy, but they're in the 1720. We had the Iroquois Six Nations, and the different Indian tribes were Seneca, Cayuga, Onondaga, Tuscarora. She grew up in New York State, so she knows more of this. Oneida and Mohawk. And so Mohawks, they were the land, Schenectady is in this area. And so it's originally the land of the Mohawk tribe of the Iroquois Nation. It was settled by the Dutch in the middle of the 17th century, and the Mohawks called their settlement Schenectady. And it means, people say different things, but it means over the pine plains or beyond the pines. That's the meaning of it. It is a sort of Dutch version of Mohawk language name for Schenectady. So it was settled in 1661 as part of New Netherlands. A famous case where they were fighting between the French and the Dutch, and the town was attacked and burned down in 1690. It was incorporated as a borough. A borough is like a city in 1765, and it was chartered as a city in 1798. So for us, this is a very old settlement, an old community, but we know that it's not old for you. This picture down here is one of the historic areas in Schenectady called the Stockade. It was the original settlement. We have this big river that goes through called the Mohawk River, and this was sort of the original settlement that was there. So we're famous for some founding companies. It was once known as the city that lights and hauls the world. So it is the Edison Electric Company, which is now known as General Electric, was started there. So I think it grew up there. So we are known for a very, very large, in the area is General Electric, which was one of the largest employers in the 70s. Certainly. Not as much anymore. We have a large steam turbine plant. They make the big steam turbines in Schenectady. And we also have in Niskayuna, which is a town near Schenectady, there's a research and development lab run by General Electric. So that's the city that lights. And then the city that hauls the world. Haul means to move, because they're also the home of the American Locomotive Company, Alco. They built trains there. This is an old picture of General Electric and one of the Schenectady locomotive works. Alcoa is out of business, so it's no longer there. They've removed all remnants of it, except some signs. And so Union College is one of the oldest schools in the United States. not as old as Perugia, but it was founded in 1975 in 1795 in Schenectady. And in fact, Mary and I, we started in 1992, and 3 years in, we had a big celebration. It's bicentennial, 200 years old. So this is just a picture of downtown Schenectady, the main street. It's a small city. About I don't know the population. Yeah, smaller than Perugia, much smaller than Perugia. So that's sort of the one main street, and yeah, there it is at night. Okay, so then Union College is, let's see where, Schenectady is over sort of in this corner down here. So we're very close. Union College was founded in the downtown of Schenectady, but moved to 100 acres plot a little bit outside of the city. And so we are a college, it's a liberal arts college with engineering. And in the United States, we have universities and colleges. And colleges are all undergraduates, bachelor's level students. So we do not have graduate level students, not master's or PhD students at Union College. It's also a residential college. The students live in, these are dormitories where the students live. So they live on the campus, and there are about 2,200 undergraduate bachelor students. And there are many more places where they live. This is not enough for all of them. It was a planned campus. So it was designed by an architect, the layout of the campus. Our central, and I'll talk about this, is this building, which was on my first slide. We're very proud of it. It's called the Knott Memorial. I'll talk about that in a minute. And then the plan was laid out. We have a library and the 2 academic buildings, and then it was built with these academic buildings. And then later they added all these other things in the background because they got bigger. The Knott Memorial is, it's spelled like this because our first, was he the first? No, he was not. You know this history better than me. We had a president of the college named Eliphalet Knott. He was president for over 70 years. And during his time, they started the building of this Knott Memorial. It was finished, I think, in 1879. And so it's 16-sided building. It is in the United States, we have something called the National Historic Landmark. So it's preserved. People can't take it, they can't tear it down. It's preserved forever. When we arrived on campus, it was in bad repair, and they fixed it up in around 1990.
For the bicentennial.
Yeah, for the bicentennial, 1995. This is the inside of it. It is a lecture space on the bottom, a study space for students on the top, and a museum or display area in the middle. These tiles, are they from Italy? I think they are.
I'm not sure. They're from somewhere in Europe, and when they when they were doing the repair, some of the tile was not in good shape. But the place where the tile had been purchased in the 1800s was still in business and was able to make the same pattern so that they could replace the tiles with the exact same pattern from the same location. But I don't remember where it was.
I'm not sure
in
yet.
Europe.
Yeah. Anyway, so we're very proud of this building. This is, but this is our Science and Engineering Center. This is a brand new building built on the campus, right across from a very old building, and that is my office. So I get to look out on a very beautiful new building. And this is the aerogel lab. So our lab associated with that building is also a science center, and we are located next to that. So this is our laboratory. The research that we do at Union, again, it's interdisciplinary, mechanical engineering and chemistry. It was established in 2002 for funding from our big science agency, which is called the National Science Agency, and from a program through the American Chemical Society. And over the years, we've had over 170 students involved in research, primarily undergraduate students, so bachelor's level students. Some of them start in their first year in college and stay sometimes till they graduate, and sometimes a little bit after they graduate if they're going to go to graduate school. So this was our group 2 years ago. This was us last year, of course, because we couldn't meet in person, so we were online. So some of the things we do, and some of these things we'll be talking about, we do some fundamental studies. We try to understand, you know, as you'll learn, and maybe some of you already know, aerogels are nanoporous. There's a lot of interesting applications because of that with high surface area. And so we try to understand how gas will flow or diffuse through an aerogel. And we look a lot at the structural changes to aerogels when you heat them up. We've got two kind of applied areas that we work in. The first listed here is catalytic aerogels. And I will talk about that work at the end. Our idea is to use these in automotive exhaust systems for pollution mitigation. Then the idea there is that they use precious group metals in automobile the catalytic converters is what we call them. And could we replace that with aerogel because of its high surface area? So we work on tailoring the composition, preparing them. You know, an aerogel on its own is quite fragile. Can you put it on some sort of external support structure to give it strength? And then testing these under realistic conditions that if you had it on a car, could it perform under those conditions? And then our other big area is working with silica aerogels, which is a lot of what we're going to talk about, especially today and this week. And the projects we've had involve sustainable window development with Professor Buratti. We're also looking at aesthetically enhanced aerogel windows with the company that we founded. We're interested in hydrophobic aerogels, and we're interested in gas sensor kind of work. Those are some of the things. Okay, and then just to finish introducing us, we did found a company called Sun Through. The idea was the sun came through the windows, or the aerogels, anyways. We founded it as part of a program that our National Science Foundation runs to get researchers out of their lab and talking to people who might be interested in businesses and companies that might be interested in their research. And so we founded this company, and we have patents on the process, so we licensed that. We are currently, 2 of the students who studied in our lab at Union College and worked with us are now our CEO, Chief Executive Officer, and Chief is really operating officer. Anyway, they're kind of leading it. And Professor Carroll and I serve as technical and scientific advisors on the grant. And so we've had some luck with some funding from our National Science Foundation and from a New York State Energy Research and Development Agency. John and Adam have won some competitions for small companies. And so we're starting to develop some high performance windows. We've switched from daylighting to actual vision lighting, and you'll see some of our aerogels coming up. And finally, why are we here? As Professor Buratti mentioned, both Professor Carroll and I are Fulbright specialists, and Professor Buratti could only host one of them, so I had the time this term to come for longer. And the Fulbright, again, it's the U.S. State Department funds the program to bring people over. We have had a long-term collaboration with Professor Buratti and her group, and have hosted Francesca Merli, Margarita Vescarelli, and Costanza, pictured here in front of our not memorial, proof that she came to see us and spent some time with us. So we've hosted the three of them at Union. Okay, I think, yes, okay. So we just wanted to stop here and ask you to, do you have any questions for us just on the introduction? And perhaps we can have you tell us who you are, maybe what you are studying here. What is your thesis work on, your research on would be good, and maybe where you're from if you're not from Perugia would be good. And I'm gonna, let's see, how do we go back? That's it. Okay. Oh,
Yep.
all right. I see people. So,
because one thing that we don't know is, we know that you are in a very interdisciplinary doctoral program. And so we suspect that you come from different backgrounds initially, and we don't know exactly, whether most of you are engineers, most of you are scientists. It would be useful to know that in terms of planning out some of the subsequent lectures also. So we've got to call on people.
Sure. Let's see. Per Giovanni is going to go first.
Okay, may I start? Yeah, okay. So, hi to everyone. I'm Pier Giovanni Domenichini. I'm a PhD student or better candidate here in University of Perugia. My background, I took my degree in architecture and building engineer at the University of Perugia. And then now I'm working on acoustics mainly, musical acoustics and architectural acoustics. My research focus on, let's say, the sustainable of the pipe organs, because I'm working on musical acoustics to try to find out what are the influences of temperature and relative humidity on the sound production of pipe organs, to try to fix some problem on the sound production, and possibly also to get longer the life of these very expensive kind of instruments. And at the same time, I'm working on how this kind of big instruments can face or are interconnected with the space that surround them. So this is why I'm studying also architectural acoustic of churches. And at the moment I'm talking to you from Sorbonne University in Paris, because I'm visiting PhD student here, and I'm working on acoustic directivity of pipe organs to try to understand how these kind of instruments developing their sounds propagations inside the churches. That's it.
How long are you at the Sorbonne for?
I was here since January,
Okay.
so a couple of months ago. I'm here until this month, so the next month I get back to Italy. So
Thank you.
Thank you.
So to have another volunteer. Shall we call? How about,
Here we go.
Giacomo?
Good morning. Good
Good morning.
morning.
You're a little bit pixelated.
Yep.
There we go. We can't hear you. I think there's a connectivity problem.
Can you hear me?
Now we can hear.
Can you hear me?
Yes.
Yes. And
No, we can't, maybe turn off your camera, maybe, it might be better without your camera.
There's a band.
I'm Giacomo.
Okay,
I'm from a little town near Perugia called Gualdo Tadino. And I'm good morning. And I'm a second year PhD student. Can you maybe if I do it better, I don't know. Can you hear me well? Okay, okay.
you're cutting out, maybe
Yes, I try to stop the video. Maybe
yes, maybe
better.
stop video. Okay,
Yeah, if you can't, I try to. Okay, can you
That's better.
hear you again?
So I think he logged out and is coming back in.
okay.
So in the meantime, should we make Francesco go since he's in the room? Right. So, yes, please.
Yes,
I'm Francesco Spaccini. My first year in PhD. My background is an agricultural one, so I am an agronomist. I graduated last year and I did my final thesis in Latvia, in Riga, capital of Latvia. And I studied a life cycle assessment, so LCA, about equality plant linked in a biogas plant. So the production of sustainable energy with biomass, that was an equality. Nowadays, in this PhD, I'm working mainly in the production of energy. Bioethanol is a biofuel. Starting with waste, agricultural waste, for example, cherry-tree rinds, olive tree rinds, maybe I don't know, pistachio husk. So I'm studying this sustainable way to produce energy, basically.
Okay, thank you.
You're welcome.
okay. Let's see, how about Maria Julia? Can you introduce yourself? Is she there?
Well, she's muted.
All right. Let's see. We lost Giacomo. Did he come back?
No, I think we've still lost Giacomo.
How about Syed? Syed? Are you there? Good. Good morning. Could you introduce yourself? Thank you. Good morning.
Yes, thank you. Good morning, everyone. I am Said Bouzid from University of Agadir. I have my PhD last year in material based on the material biomaterial based on the plaster and fibers. I work in the thermal and acoustics building and solution. I continued my PhD with the Professor Buratti in Perugia University to continue my research topic.
Great, thank you.
Thank you.
Thank you.
Okay.
We have Giacomo back again.
Yes, can you hear me now?
Oh,
Yes.
that's much better. Well, that's much better. Now we're static, unfortunately. Perhaps we'll have to have you do your introduction another time. I'm
Yes.
hoping that you're from us clearly.
Okay. How about, we know Costanza, but we would like an update on Costanza. Costanza?
I'm wondering if our sound is there.
No. Okay. All right. Is there anybody else there that would like to introduce themselves?
Yeah.
All right.
If there's the hand raising feature, could you please raise your hands if you can hear us? We're concerned that you might not be able to hear us.
Okay.
Okay,
Oh, yes.
all right,
yes.
hands
Thank
are
you.
up. Thank you.
Thank you. Okay. Do we want to take a break before we start the next part? Oh, no, sorry.
No,
No, we have a few more slides of intro. And then we'll take a short break before we start on sol gel chemistry. So, okay. So just some background on aerogels. And I'm guessing from the different things for some of you are familiar, maybe some more familiar and maybe some less familiar. Most of you are likely know what they are. So they're nanoporous, low density materials. They have an interesting, unique nanostructure, which yields interesting properties or remarkable properties. So this picture over here, some people call this the Mona Lisa of the aerogel world, and my apologies to Italian for calling it the Mona Lisa, but people talk about this, the Mona Lisa, because this is an aerogel and a flower and a flame. And so this picture is shown out there. In fact, this is the picture that a mechanical engineering student saw in 2001 and came to me and said, for our bachelor's level students do a thesis their last year. And he saw this picture and he came to me and he said, I want to make this. And I said, that's interesting. I don't even know what that is. But he was a very, very good student. And I told him that I knew a chemist, Professor Carroll. And that's kind of kicked off our whole collaboration of work 20 years ago. So here's another picture. Everybody thinks, and I myself have already said, that aerogels are very fragile, and indeed they are very fragile, but they can hold 10,000 times their weight, but they don't weigh anything. So that doesn't mean a lot, but it is true. They're very good in compression. So there's an aerogel down here with a brick on it, and it's holding it up just fine. If you try to pull on it, it doesn't do so well. And then there was I don't know if you know the Guinness World Records, the thing. Somebody probably from, I think this is one of the United States labs where they did a lot of work, jet propulsion lab, did a lot of work with aerogels. They got the certificate for the lightest solid. I think that's been usurped by now.
By a
graphene, yeah. But back then I got it, so. Okay, so just an overview of aerogel properties. So they are among the lightest known solids, and their density, depending on what sort of aerogel and what processing you use, is as low as 3 milligrams per centimeter cube and can be as high as 350 milligrams per centimeter cube. And, just for reference, air is only 1.3 milligrams per centimeter cube, so very, very low density. They are really, really good insulators, depending again on the type of aerogel. The thermal conductivity is, I've seen people talk about as low as 8. Our aerogels aren't that low, but ours are about 25 milliwatts per meter Kelvin. Okay, so 8 to 50 is kind of the range. Again, air is about 25, copper is 400,000, so that puts it in reference. Very low conductivity material. Silica aerogels can be transparent or highly transparent. They're not perfectly transparent, but they can be made quite transparent, which makes them attractive in window applications. They also have a very high surface area to mass ratio, up to 1,000 meters squared per gram of material. So because of the porous nature, the nanoporous nature of the material, and this is a sort of schematic or cartoon representation of what the aerogel structure looks like. Where these are the clusters of the silica, how they're joined. And because of that, you can end up with a lot of surface area. The surface area of each one of these clusters adds up to 1,000 meters squared per gram. And then the majority of the pore size is in the 2 to 50 nanometer range. I'm going to show it again schematically here. So those are sort of the fact that they have these properties, all of these properties in one material, is what makes them somewhat unique. This is a plot of the number of publications about aerogels versus time since it started in 2005, but they were first invented in the 1930s when somebody figured out how they use supercritical extraction to make these materials. And as you'll learn, they are difficult to make, and they were difficult back then. In the 1970s, we had more work happening with the silica aerogels. Late 1980s, the carbon type aerogels became of interest. And now in the 2010s, we start to see novel aerogels, they make graphene aerogels, carbon nanotubes, sort of all sorts of interesting things. And then in 2011, there's a lot of polymer aerogels that are being made by NASA. Again, that's one of our government agencies. And so sort of the number of publications has risen over the years, and this is low in 2016 because I think it was halfway through 2016 when he did this. So, but if you continue on, it's grown enormously. And then finally, just some background applications for aerogels. They're used, they have potential use in many areas. Commercial use is growing. Originally, they were just too expensive to use commercially, and they were used in space applications. This is the NASA Pathfinder that went to Mars, and they used aerogel for the insulation. Why? And you can afford to use an expensive material because it's lightweight and it's very insulating. And if you're sending something to Mars, you need it. It also was used to collect comet dust because of the low density. And this is a trace. So they had a satellite out there with tiles made of aerogel going through space, and they could collect dust in the aerogel, and these are little dust particles. And because of the low density, you're able to do that without damaging the materials. And they brought it back to the Earth, and they had a large citizen science program where you could go on and look at their images and identify dust particles. And I did that for quite a while, and I found one. Well, I found a potential one. I think I got one. Anyways, other applications, of course, so insulating. A big commercial application area is in blankets. A company in the United States called Aspen Aerogel produces, and also Cabot produces aerogel blankets, and they can be used to insulate pipes and things like that. That's one way they're used. The windows, we'll talk about windows. Originally, the types of aerogels that were used were granular. They are not transparent. They are opaque. You can get some light through them, so they were used sort of in places where you didn't need to see out. But now there's been much more work with transparent. Chemical sensors, another area, and acoustic absorbers, which I know is of interest to people. So, okay. So I think what we want to
coffee break.
Yeah, this is coffee or bathroom break. We will start at 10 o'clock. And Professor Carroll is going to talk about some of the chemistry related to aerogels. Want to say anything else?
No, I mean, I'll do the introduction of that and we'll talk specifically about silica aerogel chemistry, but we will meet again in a few minutes. We'll leave everything on so
Yes.
we don't accidentally lose you.
Yes. So we'll start again at, it's,
Oh, gosh,
oh, thank you.
Can you still hear us? Could you put the little hands up?
Okay.
Okay, all
Okay.
right.
We're not sharing screen because I closed it, but we will share again. Well, let's actually load it up and
We've
then we'll
got
start,
a separate presentation. We'll start
at
10
10,
o'clock.
10
Okay.
o'clock. Okay. Do that. Let's get that up there.
Let's usually take a break.
Okay.
Is it usually longer than we just said, or is that?
It's very longer, but also the class is longer.
Oh, okay.
So, answer you just 2 hours, I think, at 5 minutes.
Okay.
Okay.
Thank you for the rest.
Yeah.
See you in.
Yes, yes, yeah. I just said that because it was too close to 10. All right, how am I not getting this introduction?
So you've got to put the,
Let me just close it.
and then
Yeah.
the salt, you want the salt gel chemistry one.
Right. All right, so
Okay,
then
now
we
you
do
have to get it so
presentation
that you
mode,
presentation mode, and then you have to.
escape, Teams, this.
There we go.
Okay.
Okay. Yep. And I'll trade seats with you. I'll move your stuff over. Oh. Got a copy? Oh, that's interesting. That's not bad. Hmm? We're all set.
You want to mute? Mute it? I don't know.
How do we see how many people there are? What do we do? Do I want to do that or not? Just leave it where it is? Oh, there we go. Oh, we have more people now. He's doing it behind the scenes.
Right.
Okay. So, and then I just minimize it here,
Yes.
and then
No,
Nope.
did the max one. The little, oh, you don't have that in?
Hmm?
That Max don't have the big?
yeah, we do
Okay.
different sizes.
You could ask anyone else who says something about their research.
Okay, so before we get started again, we know that some people had connectivity problems before. And if anybody would like to introduce themselves and their background and their research project, we would be happy to hear about that. The other question I have, as I'm starting the discussion about sol-gel chemistry, from what I've heard of backgrounds, I'm assuming that you've had some chemistry, but that it has not been a major focus of your studies. And so I have planned this portion of the lecture at a very basic level. If it turns out that you're finding this to be too basic, please let me know before we do more chemistry on Thursday. But my assumption is that you all have backgrounds where you're using different materials, that we want to know something about how those materials are made, and that we're going to have to use some chemistry to do that, but that may not have been your
I want
focus.
to confirm they can hear you.
So can you confirm that you
Maybe
can hear me?
Hands up, somebody?
So could we have hands up if yes, you can
Okay.
hear? Okay, terrific. And one last time, anybody want to do an introduction at this point, or are we ready to talk about some chemistry? Okay, I'm not seeing any hands up or anybody unmuting, so I'm gonna move on to talk about chemistry. maybe. All right. So one of the things that I want to talk about is some of the terminology that we're going to be using over the course of these lectures, not just on the chemistry, but some of the terminology we're using. And most aerogels are fabricated using sol gel processes. And so I thought I should go through what all of those particular terms refer to. So the term sol gel refers to a process in which we have a solution, it's a heterogeneous solution of nanoparticles dispersed in a liquid, which is known as a sol, and which we will talk about more in another couple of slides, agglomerate together, so join together to form a continuous network that extends through the liquid, so that it forms from a sol into a gel. And that's the terminology. The term sol gel is then sometimes used to refer to the materials that are made through this process. This isn't actually literally correct because it is no longer a sol. And it also isn't very specific because it doesn't tell us much about the material itself. When we have the initial gel that has the liquid in the pores, it would be better to call it a wet gel or an alkagel, which reflects the fact that it tends to have alcohol in the pores. After drying, the pores of the gel are filled with air, and depending on how the drying process has occurred, we may have a xerogel, which is a shrunken dry gel, or an aerogel that maintains ideally the same size. So sol gel materials encompass all of these things, both the wet gel materials and the various dry materials. And so it's not a very specific term, but it is one that you will see. Okay? A sol is a type of colloid, and colloids are mixtures in which you have two different components mixed at a nano level. Now, colloids can be in different phases, and in the types of colloids that are used in the sol gel process, we're dealing with a liquid phase. Typically, we have some sort of phase, you could think of it as a solvent, in which something else is dispersed. And those components that are dispersed are generally at a nano or micro level. It could be nanoparticles, it could be macromolecules, and some everyday examples of colloids include butter and margarine, which contain both aqueous species and oils, which normally wouldn't mix, but because there are other chemicals in there that are known as emulsifiers, you can get a suspension. And so, you know, your things don't settle out of the butter or settle out of the mayonnaise because it's in this colloidal suspension. Okay. Now, of course, we're not making aerogels out of butter or mayonnaise, right? We're going to use some other things. So a sol, just coming back to that term, is a type of colloidal mixture. And so the continuous phase when we have a sol is a liquid, and the dispersed phase is a solid. That can be a liquid mixture. It's not always a pure liquid. And the solid nanoparticles are suspended throughout the liquid. They're not settling out. So we have it's not a homogeneous solution because we have the different components, but we do have them suspended. And an example is inkjet ink, where you have a liquid, it could be water, you have something like carbon black dispersed in it, but it's dispersed in a fairly uniform way at a really pretty small scale. Okay, so when we have a gel, we have a wet material where we have some solid structure interconnected, and the pores are filled with liquid. And so an everyday example of a gel would be Jello. Do you have Jello in Italy? Jello, gelatin, you mix it up. Yeah, it's the same brand name. Okay. So what you have is this solid network, but it had all of the pores are filled with liquid. Now, they can be squishy, right? Or not, they can be more solid, but they tend to be more than 90% liquid in composition. And so overall, the gel is going, if you looked at the properties of the gel, they would most resemble that of the liquid, but they have a certain cohesiveness, right? So you can make you can cut pieces of gelatin out, right? You can have individual pieces, and the structure is maintained because of the solid network. And again, we're not making aerogels out of gelatin, but this is the same general idea. So if we have a gel and we let it dry under conditions that result in it shrinking as the liquid evaporates, and Anne will talk more about this, I believe, in tomorrow's lecture, and there tends to be pore collapse because capillary action, okay, and the evaporation. If we have that happen and we let it dry all the way, we will still have the solid, but it'll be shrunk down into a smaller area to be higher density, and it's known as a zero gel, where XERO it's a Greek prefix meaning dry. An aerogel is a porous solid matrix where if we have the sol, form a gel, and then are able to get the liquid out of the gel without collapsing the pores, we would be left with the same porous solid matrix, but all of the pores are filled with air. And as a consequence, the vast majority of the aerogel is air by volume. There's 1 to 10% solid by volume, and this is what gives it some of its really interesting properties. It's not particularly easy to get the gel to an aerogel without having the pores collapse. And so when Anne and I started collaborating, I was already working with zero gel materials. She mentioned a student came to her and she didn't know what an aerogel was, and sent the student to me, and I said, well, I know what an aerogel is because I've been working with these sorts of materials, but we don't have the equipment to make them. And that's how we started collaborating, and it's one of the ways that we ended up inventing a new process, is that we did not have the traditional equipment to make aerogels. And so we used equipment that we had on hand, and Anne will talk about that in some detail tomorrow. So here's another sort of cartoon representation of the difference between a wet gel and aerogel. And again, ideally the aerogel would have no shrinkage, so little to no shrinkage, so the network would still be there. Each of these sort of spheres represents the colloids. So we have, these are not representing individual atoms, right? This is representing a cluster of, in the case of today's lecture, silica material, right, that was in the sol. So when we had the sol, I'm going to go back to the other cartoon, we had these clusters. This is not to scale, obviously, because we would be looking at nanoparticles, so they'd really be much smaller. Okay? So we're looking at individual clusters of, in this case, silica, starting to link together chemically to make this overall network. And so the wet gel, the aerogel, the zero gel, these are all really polymeric materials by the time they're formed. They're just being formed through the sol gel process. And the difference again between the aerogel and the zero gel is that the zero gel has undergone some pore collapse and therefore is a smaller size. So how do we actually make silica gels with the sol gel process? So I just want to check, can you hear me? Because I'm seeing disactivate the microphone wording up here, and I'm not sure how to get rid of it.
I think it's
It's gone now. Okay. So I think they can hear me. Okay. Typically, we use silica alkoxides, which are compounds that have the formula silicon with 4 oxygens connected to the silicon atom and some sort of organic group attached to the other side of the oxygen. And these are usually most commonly used as the precursors to make the 3D networks of silica. And the way that this happens, these compounds do not react with each other normally. We have to do 2 types of reaction in order to make the sol and then make the gel. And so the first reaction is hydrolysis type of reaction, which is a reaction of the silica alkoxide with water. to yield some hydroxyl groups, and then condensation reactions, and it's multiple condensation reactions, first creating the colloidal particles and subsequently linking the colloidal particles together to make the extended polymer structure. So sometimes you'll see in papers hydrolysis and polycondensation. Polycondensation just means we're doing a lot of condensation reactions to make polymers. It's not strictly speaking necessary to say polycondensation, but it emphasizes that there's more than one of those going on. And so just to orient everybody with the structures, again, I said we're going to have a silicon. So this is one of the most commonly used compounds. That's shorthand is TMOS. It's a silicon, 4 oxygens connected to silicon, and then a methyl group, a CH3 group on each of them. I'm going to be using the line structures, which I'm sure you've seen before, but if you haven't been seeing them recently, I'm going to go through that. I'm just looking for confirmation in the room. Make sense? Or is this obvious?
Not really obvious.
It is not obvious. Okay, good. No, that's fine. I was planning to talk everybody through this. So here's my silicon atom, connected, bonded to 4 different oxygens. And then at the end here, I have a carbon. So line structures are sort of like stick figures for chemists. And if you're going to make a stick figure, you'd have a head and a body and some arms, and basically you're not showing all of the parts. But it's a representation that somebody else will look at and say, oh, they're representing a person. The same idea with these molecules. There are more and less interesting parts of the molecules in terms of the chemistry. And we refer to these as functional groups, the groups of atoms that are giving the function, the chemical and physical properties of the compound. And structure determines function, and there are certain parts of the molecule that are more interesting than others. And in general, hydrocarbons are not terribly interesting, right? Unless you want a fuel, right? You're going to burn them, then they're very interesting. But carbon to carbon bonds, single bonds, and carbon to hydrogen single bonds are not particularly reactive. They are not going to be the parts of the molecule that are most interesting in the chemistry. And the line structures de-emphasize those. So carbon normally forms 4 bonds, and a lot of structures that have organic things in them have carbons, and so we de-emphasize them in the structure. So when we have a position like right here, where we don't have an atom labeled, it's a carbon. And here at this end, I don't have an atom labeled, it's another carbon. And carbons usually make 4 bonds, but the carbon-hydrogen bonds are not particularly interesting in terms of chemistry, so we don't show them. So this carbon here in this location, I can see it has a bond to an oxygen. I can see it has a bond to another carbon. That means it must have 2 hydrogens. This is a carbon. I'm only showing 1 bond to another carbon. I'm not showing any bonds to anything else, so it has 3 hydrogens. But again, these aren't the most interesting part of the molecule. The more interesting part of the molecule is at the center. And so the line structures show all atoms that are not carbon and are not hydrogens attached to carbons. So if I have a hydrogen attached to something other than a carbon, I will show it. But I never show the hydrogens attached to the carbons. And it just makes it easier as the molecules get bigger to represent them. For very small molecules, I could put the C with all the H's, and in one of the next slides, you'll see that. It's just, you end up with a little bit of extra space being taken up in all of the drawings with the H's. So this is TMOS tetramethyl, so it means 4 tetramethyl orthosilicate, so 4 methyls on an orthosilicate. And unfortunately, we're not always consistent in nomenclature. It can also be called tetramethoxysilane. So this is because the silicon oxygens is a silane type of compound. 4 methoxys, which is a CH3 attached to an O attached to the silicon. Another thing I need to note is that when we're drawing chemical structures, we're taking a 3-dimensional structure and we're drawing it flat on the page. And so the chemical structure that I show is not necessarily representative of the actual geometry of the compound. And in particular, if I think about these bonds around the silicon, there are 4 different bonds from the silicon atom to an oxygen. Each of those bonds involves 2 electrons. And so there's going to be a region of space in which the electrons are found, an orbital here. But the electrons in any one of these bonds are going to repel the electrons from the other bonds. So they are going to try to get as far away from each other in 3-dimensional space as they can. And the farthest that 4 groups can get away from each other in 3-dimensional space is in a tetrahedral configuration. And so if all 4 of the groups are the same, which is the case in the TMOS, the tetramethyl orthosilicate, and also in the TEOS, tetraethyl, where I have what's called an ethyl group, a CH2CH3 group attached to the oxygen, they're going to have nearly perfect tetrahedral geometry around the silicon with about 109.5 degrees. What that means, though, is that we have a 3-dimensionality around this. And as we're thinking about making a gel, we don't want the gel to extend only in 2 dimensions. You want the gel matrix to be building in all 3 dimensions. And so starting with a precursor that has a geometry that isn't flat is one way to achieve that. Before I go on, are there any questions? We'll be seeing some more line structures. Questions about line structures in general? Okay. So, as promised, here's a drawing where I'm actually showing all of the carbons and hydrogens, and you see that it's starting to get kind of cluttered, right, to try to fit them all in. But here's TMOS again. So we have the methoxy, the oxygen with the methyl group. These, and I don't think I said it on the previous slide, TMOS, TEOS, most of the silica alkoxide precursors are liquids at room temperature and pressure. And so they can be easily worked with in terms of making measurements either by volume or by mass. And they're easy to do. So we'd mix the various ingredients. I'll come back to what those are. The first thing that has to happen, though, is if I have a bunch of TMOS surrounded by other TMOS, it's not going to do anything. It's not going to make a gel. I'm going to have to first hydrolyze it and then allow the condensation reactions to happen. The hydrolysis reaction is the reaction of these methoxy groups, or ethoxy, or whatever the substituent is, the OR group, with water. And so what we had, if we did a single reaction, one of the groups would react with water, and instead of having an O methyl or O ethyl or O something else, we would end up with an OH. And if we did this a bunch of times, we might end up with more hydroxyl groups. The net result is that we're going to then also make an alcohol molecule. And so hydrolysis just means reaction with water, so it's a very general term. In this case, what we're talking about is the hydrolysis of the metal alkoxide, in this case a silicon alkoxide with water, to make a metal hydroxide. And I'm going to have a couple line structure examples on the next slide. If I can get to the next slide. All right, so here again is the line structure of TMOS. And if I react 1 molecule of TMOS with 1 molecule of water, I can make a substitution here. Or basically, I've got the O methyl and a hydrogen reacting to make, this is a CH3OH. This is methanol, a very common alcohol. It's known as wood alcohol sometimes. Methanol, and now I have 3 O methyl groups here and an OH group. This is more reactive, and this is what's going to allow us to do the subsequent condensation reactions. I can do this once, or I could do this as many as 4 times, and I could end up with OHs in each location. If it did it 4 times, I would end up with 4 methanol molecules. If instead I use TEOS, the tetraethyl orthosilicate, I have the CH2, CH3 here, react with water. The same sort of reaction occurs. I end up with the hydroxyl group, the OH group, or the alcohol group. I can call them any of those. And I end up with CH3, CH2, OH, which is ethanol, which is drinking alcohol, right? The alcohol. So depending on which alkoxide I use, and there are many other silica alkoxides, they could have longer groups, they could have branched groups, there's a bunch of different things that could happen. I will make a different alcohol as a result. But I'm trying to hydrolyze the alkoxides so that I can do subsequent reactions. So in this case, the alcohols are just considered byproducts of the reaction, and they would be left in, in the mixture, and they'd end up in the liquid portion of the gel that's eventually formed. So after we have hydrolysis, we then have to do condensation reactions. And what we're wanting to do is end up with a network that is essentially silica, SiO, and then the next thing it would be connected to is another Si. And so the network would be silicon to oxygen to silicon to oxygen, and potentially an individual silicon could be connected through oxygens to 4 other silicons in a 3-dimensional matrix. Now, the condensation reactions can actually happen a couple of different ways, but what we're trying to do is get these clusters of silica to form and start linking together. So we form the sol and link together to make the 3-dimensional network. And again, I'm going to show this with some line structures. So here are some condensation reactions. I'm starting with the alcohol species, the hydroxyl species, the OH species that's here. And if I have 2 silicons, each of which have now got an OH group, it's possible for those groups to react together, splitting out a little molecule with both of the hydrogens and one of the oxygens, so water, and linking the silicon atoms together. So now I would have the silicon-oxygen-silicon bond, so that's a metal oxide sort of bond. Each of them I'm now showing still connected to a methoxy group, but you can imagine that if there was another OH here, it could then link to another, and another, and another, making an overall 3-dimensional structure. If we do the same thing with our hydrolyzed TiOS, we end up with a silicon-oxygen-silicon bond, and we split out a water molecule. This is one of the types of condensation reactions that will occur in the mixture that we have, because if we have hydrolyzed multiple species, they can react with each other. But we can also do condensation reactions between one of the hydrolyzed species and one of the original species that hasn't been hydrolyzed. So the OH group here can react, in this case, with the O-methyl group in a similar way that the water had reacted in the hydrolysis step, right? We had water reacting with this to attach a hydrogen. In this case, we're going to have the oxygen is going to end up being bridging between the silicon to silicon again. But now the hydrogen and one of the oxygens and the CH3, so the CH3OH is going to make another methanol. And so our condensation reactions could be between 2 hydroxyl groups, or they could be between the substituent group on the original alkoxy silane and a hydroxyl group. And here again is an example with TiOS. So now TiOS that has been hydrolyzed reacting with an unhydrolyzed TiOS, and again we get the silicon-oxygen-silicon link. Now, I am not trying to show geometry here. Again, I'm showing 3-dimensional molecules in 2 dimensions. So the fact that this looks like a straight line and this doesn't look like a straight line doesn't mean anything. It's just the way that the drawing program drew them in that particular case. Neither one of these shows the true structure because neither one of these is showing 3-dimensionality. Okay, this is not a T shape here either. In this case, we would end up with ethanol. And so I'm going to skip back a couple slides just to say again, in hydrolysis, we end up making alcohols. the condensation reactions, we end up with water and with an alcohol as the byproduct. And so in the gel that we eventually make, as these reactions happen over and over again with all of the different branches, and we make the three-dimensional structure, we are adding solvent as well to the situation. So we're going to have made a solid network, and the pores are going to be filled with liquid. That liquid will be from the byproduct of the reaction, and the liquid will also be from solvents that were present in the mixture that we use. And these are the basic reactions that cause this. Now, we will talk about some other chemistry on Thursday, and they will be slightly different chemistries, but the general idea is this: we are trying to link together smaller species to make a network, usually with the metals, an oxide-based network, and it's a little bit different with carbon aerogels. It'll be a carbon three-dimensional network. So there's a couple complicating factors. And one is that silica alkoxides are not soluble in water. And since the first part of this process requires the silica alkoxide to react with water, this is problematic, right? If you just put the silica alkoxide and water together, it's like an oil and water thing. You'll have two levels. The only place the reaction can occur is at the intersection of those two different layers. And so that's not the best way to try to do a reaction that you need to have to start this whole process. And on top of that, even if you can get the silica alkoxide and the water next to each other, the hydrolysis and condensation reactions do not proceed very quickly unless we use catalysts to speed the reaction. And a catalyst is a species that speeds a reaction by providing a lower energy mechanism for the chemical reaction to occur. There are two general categories of catalysts. There's homogeneous or homogeneous catalysts. I'm going to say it both ways because both pronunciations are acceptable. And there's heterogeneous catalysis as well. In this particular case, we're going to use homogeneous catalysis. We need a catalyst that's dissolved within the mixture because we need these reactions to be happening throughout the mixture. And heterogeneous catalysts are in a different phase than the reaction. And the typical type of heterogeneous catalyst, it's a solid onto which the different chemical species adsorb, and then it is easier for them to react. Catalytic converters in cars use heterogeneous catalysts. So the gas molecules adsorb onto the catalyst. That makes it easier for bonds to break and reform. But here we need a catalyst that can be within the whole solution. We need this to be happening not at one surface and lifting off. We want it to be happening throughout the whole thing. So the recipes for making silica gels include not just the silica alkoxide and the water. We also have usually an alcohol added, and we add an alcohol because silica alkoxides are soluble in alcohols. Water is soluble in alcohols. And so if you have the alcohol in there, you can get the silica alkoxide and the water closer together than if the alcohol wasn't there. And we typically use aqueous acids, so water phase acids and or bases also. And so some of the water that we're using is coming in a solution that might contain ammonia or might contain some sort of acid typically employed. And so this makes it a little bit easier to do the reactions. So I'm going to show you a couple of typical recipes that we use in our laboratory. One is for making TMOS-based gels. So this is the tetramethyl orthosilicate or tetramethoxysilane. These are liquids, so we can weigh them out either using analytical balances or we can pipette. The volumes that we're using for larger samples don't lend themselves well to volume measurements, but lend very well to making mass measurements. In this particular recipe, this is just, to make roughly 100 milliliters, but that's rough volume of a mixture. We'd have 26.4 grams of the TMOS, which has a density that's just, I think, a little bit higher than water, but very close to water. About 66 grams of methanol, which has a density lower than water. about 10 grams of water, and then we typically measure the catalyst out by volume because we're typically not adding very much catalyst. And so in this case, somewhat less than 2 milliliters of catalyst. We combine them. Even though we have the methanol there to help with solubility, if we do not stir it, we will still have a separation of phases. The water will still initially be in a separate layer than the other solvents, and so we stir until we observe that the mixture is now a single phase. The reaction has been happening. The stirring just gives us a mechanical exposure of the different things to each other. And then we can allow it to dry under ambient conditions, under room conditions to make xerogels, or we could process to make aerogels. This is an example. You can see the aerogel here. This is a very translucent thin silica aerogel. I believe this one is about 5 millimeters in thickness and roughly, I think this is about 100 by 100 millimeters in length. To use TIOS, which again had the longer carbon chain, we've found that a two-step catalysis approach works better. So we use an acid, in this case it's a weak acid, oxalic acid, to catalyze the hydrolysis reaction, and then we add base to catalyze the condensation reactions and result in the gel. And so again, we measure out amounts of the alkoxide. We can use ethanol. We can use different solvents. So the TIOS has the ethyl groups on it, so ethanol makes sense, but we have also made TIOS gels using methanol, deionized water, the oxalic acid, and you'll notice it looks like there's a lot less water in this recipe than the previous one, but that's not actually true, because the total amount of water in this recipe is the amount of the water plus the amount of the aqueous ammonia. This is a 1.5 molar solution. It mostly is water, even though that's reasonably concentrated. Here we have a very dilute aqueous oxalic acid solution, small amount of water by itself, and a larger amount of water coming in as the aqueous oxalic acid, and then subsequently even more water coming in the ammonia. So this recipe actually has more water. We combine the TIOS with the alcohol and the water, and the first catalyst, again, we're using the ethanol really to help us with the solubility. In this case, we mix for longer time and until it appears to be monophasic, and then we allow this to react. It seems to be a slower reaction, most likely just because those are bigger groups. And in order to have the reaction happen, the water and the TIOS have to collide in a correct orientation with enough energy to cause the reaction. And so that is not going to happen as quickly or as it would with the TMOS, with the smaller functional groups. And so we allow it to sit for about 45 minutes to do more hydrolysis. And then we add the ammonia, mix for another few minutes, and then we can let it sit until it gels. Both of these recipes under ambient conditions would typically gel, within an hour, okay, of the mixing. Or we can process them to make aerogels. And this is an example of a similar size TIOS aerogel. You can see that this one is not as translucent as the other. You can see some light through it, but it isn't as translucent as the example on the previous slide, which is highly translucent aerogel. So the optical clarity of those silica sol gels, whether we're talking about xerogels or aerogels, depends on the clusters. It depends on the size and the distribution of those clusters. And we have control, but limited control over that, right? So we can vary the precursor mixture, we can vary the catalyst concentration, we can vary the processing parameters, and we get materials with slightly different optical properties, right? Sometimes if it gels too fast, it's not very uniform. Sometimes if it gels very fast, it's cloudy. Sometimes it gels, very slowly. It depends. There are a lot of trial and error aspects to doing this sol gel chemistry. We can make a mixture that gels in ambient conditions to make a clear, colorless gel, and we can process it and sometimes get a cloudy gel, because when we're making the aerogel in another process with different temperature conditions, we can have the reactions happening at faster speed. It may be making smaller or larger clusters, the way they're coming together. And so these are the sorts of things where it is tailorable, right? You can change what you're doing to get different results, but there's a lot of trial and error associated with that. The other thing I should note is that the gels that we make from TMOS or TIOS are usually hydrophilic in general. In fact, the method we use is they're slightly less hydrophilic than some other traditional methods. The reason is that ideally when it's done, we have just a silica matrix, but there are going to be some groups still hanging off the ends, essentially, that haven't reacted. And when we've prepared them this way, those groups tend to be OH groups. And so that's going to give you some functional groups that will interact well with water. And you likely have seen silica gel, not aerogels, but silica gels used as desiccants in packaging. If you buy a pair of shoes, there's usually a little packet of silica gel in the box. You can see it in a lot of others. It's used as a desiccant, a drying agent, because silica gels are hydrophilic or water-loving, will pick up water from the air. And so that's an application for them. That is clearly a problem if you're trying to make a window, right? Because your window is likely going to have some exposure to water vapor. And so for a number of applications, that's not the only one, some hydrophobicity is desired so that we don't have water adsorbing onto the surface of the gel, changing both its optical properties, but also potentially causing pore collapse. And so I'm going to stop here for a second. I'm going to talk a little bit about how we can make these gels hydrophobic, but first I want to see if there are questions. How do I see it? I'm a Macintosh person and we're here on a PC. So does anyone have any questions about the chemistry that we've talked about so far?
They don't want to ignore the person.
Yes. Okay, so I'm going to talk about the hydrophobic, how we might make them hydrophobic. And it's very similar chemistry, is we're just going to start with some different precursors. All right, and now I have to move this because it's in the way. All right. So what we can do is use organically modified silica. We can sometimes use the term ormacil alkoxides. So instead of 4 groups around the silicon that all have an O and then something attached to them, we could have 3 or 2 or 1 groups with the O, and another group of an organic substituent that's directly connected to the silicon. So again, just talking you through the line structure, this is a silicon to an oxygen to a carbon with 3 hydrogens. Silicon to oxygen to a CH3, a carbon with 3 hydrogens, or a methyl group. This is a silicon directly bonded to a carbon that has 3 hydrogens. Or, in this case, a CH2, CH3 group, or a CH2, CH2, CH3 group. That's a propyl group. Or I could have a TIOS derivative where each of these had an ethyl or a ethoxy, if we do the whole thing, and it's got some organic substituent here. Without the oxygen, the hydrolysis reactions, the condensation reactions that I showed you before don't occur. Right, so this bond between the silicon and the carbon is not going to be broken to make an OH linkage. And so if I use one of these precursors, I'm going to end up with a material that has essentially what we would call dead ends, right? The reaction can't occur in this direction. I can't link this silicon to another silicon through here. I'm going to be stuck with a silicon attached to a carbon. And I want to make something that's hydrophobic. I want to have things on the surface, chemical species on the surface, that repel water as opposed to attract water. And these hydrocarbons, things that just contain carbon and hydrogen, are not very miscible with water. And so the fact that I'm going to end up with a material where some of the silicons have these groups on them is going to give different properties to the material. Now I'm showing examples here. These are just 4 examples, 3 which are derivatives of TMOS and 1 which is a derivative of TIOS, but there are lots and lots of others. In fact, we've authored a chapter in the Aerogels Handbook. The earlier version is a 2020, I think 2011 book. The new version, the Springer Handbook of Aerogels, is going to be coming out later this year, and there's just tables of these compounds that have been used to give hydrophobicity. Many of the compounds are hydrocarbons. There's also been work done with fluorocarbons, which you will know from non-stick pans and things like that, also repel water. They repel water and repel oil, so they have different properties. If we want to make a hydrophobic silica gel, we're going to use a similar sol gel process. But generally, these reactions are going to be more slow because now fewer than 4 of the substituents on the precursor, so around the silicon, can participate in the reaction. So to just go back for a second, I can only have hydrolysis and condensation reactions occurring here and here and here. And that means that if water molecule is going to run into this, if it runs into it over here, nothing happens. So that would be an ineffective collision. We're going to have a collision here with enough energy to react, or here or here. And so the kinetics of making hydrophobic silica aerogel are going to be slower because of that. Right? Especially if we start to have much longer chains, which will give more hydrophobicity, they're also going to get in the way of the reactions. There'll be fewer effective collisions. The network structure is also going to have fewer connections to silicon atoms because for the precursors used in Ormasil than we would have for TMOS or TIOS. With TMOS or TIOS or other ones that have 4-alkoxy groups on them, we can have the reaction occur in each of the directions, and we can make the 3-dimensional network. But with these, we can do a 3-dimensional network, but it will have fewer connections. And so to yield stronger materials and more intact monolithic materials, typically you start with a precursor mixture that contains both some sort of organically modified silica precursor and a more traditional TMOS or TIOS in order to yield stronger materials overall. And so what we would end up with, and this is a line structure of a segment of the silica network. You have a silicon attached to an oxygen, and this bracket just means, and it continues. So it continues to another silicon. Silicon to oxygen, this would continue on to another silicon and over again. But this group has some sort of substituent that couldn't participate. So we would see if we had one of these groups out of every 3 silicons, this is the sort of thing we would end up with in the structure. So it just shows a section of the silica matrix and how it now has this group which would repel water. And this is one way that we can make hydrophobic materials. Now, hydrophobic materials, I think Anne will probably cover this in a subsequent lecture, probably not this week. We can also have physical reasons that things are hydrophobic. I'm talking about the chemical reasons that they're hydrophobic. And hydrophobic silica aerogels are actually a lot of fun to play with because things happen like this is a stream of water bouncing off the aerogel surface. Water will bead up, and you can see the extent to which it beads up on the hydrophobic aerogel surface. A hydrophilic surface, the water would wet the surface. We'd either get a drop that was shaped like this or actually just a spread out on the surface even more. We look at this angle, the contact angle between where it contacts the surface and the drop. And a hydrophilic surface would have a lower angle. Hydrophobic surfaces have large angles. This drop is a super hydrophobic. It's on a super hydrophobic surface. The angle is, in this case, greater than 140 or 150 degrees. And so these are highly, can be highly hydrophobic. I'm showing some images here from an undergraduate student thesis from about 10 years ago. Again, water jumping up. It's actually very difficult for us to get some of these pictures because if the surface is not flat, the water droplets roll off the surface and you can't get the image. So you have to make sure that you get a really flat thing. We can also, this case is a ping pong ball. So from table tennis, submerged in water. And this is a ping pong ball that's been covered with hydrophobic aerogel, submerged in water, and you can see the bubbles of water surrounding it. So we've got air trapped. The water is not contacting that. Materials like this will float on completely on top of the surface of water. It wouldn't be like an ice cube. It wouldn't be partial. It would be very much repelled. And so you can see that these might have interesting applications, and we have been doing some work potentially in drag reduction for boats, coating on boats and things like that, as well as some other applications in the window area, including a current project that we have going on with Professor Buratti, where we're looking at how some hydrophobic aerogel monoliths are behaving over an accelerated aging period. And this is not our work. This is from Professor Rao in India. He took super hydrophobic aerogel, he powdered it, and then they put a drop of water down, and you end up with aerogel on the outside of the droplet. And you can roll these things around. We actually had him visit Union a number of years ago, and he demonstrated this to the students. So there's some very interesting things. I think we're right about at the end of the time, and we wanted to leave some time for questions. And frankly, one of the questions that we do want to ask is whether we are we're trying very hard not to speak too fast, but whether we know that we're introducing new material and we're speaking in English. And I wanted to ask whether you are having any difficulty understanding or following the pace as we're thinking about the next lectures. The other thing I should say, and we know this from the visitors we posted at Union, we do not have the same regional accent. We are from slightly different areas of the US. I'm from upstate New York, which is where we are. I'm from the Rochester, New York area, and Professor Anderson is from the Boston area. So we know that we are not speaking with the same accent either. And I'd like to know whether the clarity and the pace is working okay for everyone.